right, so we said that lecithin is an example of a phospholipid, and we said that the main difference between a phospholipid and a triglyceride is that a phospholipid has only 2 fatty acids, and then it has a phosphate group and something else attached. And we said that that phosphate group has a charge to it, and that something else attached has a charge, and the 2 fatty acids, no charges. The thing with a phospholipid, the second fatty acid, remember we said has to be unsaturated. First one can be saturated or unsaturated. With a triglyceride, on the other hand, there's no charges, there's no phosphate group, and you can have them all saturated, all unsaturated, whatever. All right, so there's your big difference between triglyceride and a phospholipid. Now, if you've had a biology class, you already know that your plasma membrane, your cell membrane, is made up of a phospholipid bilayer. So what I did was I drew out the stuff that you guys have seen in a biology class. Now what I want to do is relate this to the actual structure of lecithin. All right, so see these circles over here? These circles, they represent this portion of the phospholipid, the charged portion, the portion that's got the phosphate group with the negative charge and this nitrogen, this ammonium ion with the positive charge. So these heads, these are called the polar heads, polar head. And then these 2 long things, these are the 2 fatty acids. They are called the non-polar tails. Now notice that this one is kind of straight, but this one has a kink to it. That kink indicates the double bond, all right? So specifically it's a cis double bond, and cis looks like a kink. Trans is more straight, cis is more kinked. Don't worry about those details. But what you should realize is that when you see something like this from a bio class, what you're doing is you're seeing this here. This is the head. This portion is the head. And these are the 2 tails. Okay. Why is there a kink? Because the second fatty acid has a double bond in it. And these phospholipids are so important for regulating what can come in and out of the cell. Because there's such a large non-polar area here, and this is polar. Polar is looking out towards the outside of the cell. I put the word out here because outside of the cell, so mainly water. Inside of the cell, mainly water. So think of it as this is your cell, and what we did was we took a chunk of this plasma membrane, and this is it. So this is out, and this is in. So things that want to come in that are polar aren't going to be able to come in. Because there's such a big non-polar hydrophobic area that it won't come in. So for example, glucose wants to get into the cell, it won't get in. Why? Because glucose is very polar. It has lots of OH groups. It can hydrogen bond with water, very polar. But it's trying to get in, and this non-polar area, these very long fatty acids, won't let it in. So how does glucose get into the cell? We're going to talk about that when we get into metabolism. And it's because the insulin hormone comes and binds to the plasma membrane, making it more porous, allowing it in. All right. But back to the structure of a phospholipid, you should be able to tell me which part is the head, the polar head, the charged part, which part are the long non-polar tails. The cool thing about phospholipids is because they have a section that likes water and a section that doesn't like water, they work as really good emulsifiers. What's an emulsifier? An emulsifier is something that can get oil and water together and mix them up very nicely. So if you normally have, I'm going to just erase this over here. If you normally have a beaker and you put water in it and then you throw in some oil, you know that the oil will just layer on top of the water. It won't mix. And if you shake it up, it still won't mix. It'll layer out. But this emulsifier here, this polar head is attracted to the water. And these non-polar tails are attracted to the oil. So what actually will happen is that instead, if you throw in some lecithin into this, you'll still have water at the bottom and you'll still have some oil on the top. But in the middle, you'll see that a bunch of oil droplets start to suspend in the water phase. And this over here, this is called an emulsion. What's the practical application of this? Have you guys ever baked? I love to bake. It's good therapy for me. Well, you have a lot of lecithin, a lot of this phospholipid in egg yolks. And if you're baking a cake and you're throwing in some eggs, the purpose, the chemistry behind those eggs is that that egg yolk will allow whatever fat and whatever liquid to combine properly and make a nice, beautiful textured cake instead of something that has several layers to it that are not properly mixed. Okay, it would be more like rubbery if it doesn't have that egg in it. You know what? This is something you can try out for yourselves if you don't believe me. Get a jar and put some water in it and put some oil in it. Okay, and then in a bowl, separate the separate the yolks from the whites. All right, just get the yolks, maybe 2 or 3 of them, and mix them up and then throw them into that jar that has the water and the oil, and then shake it thoroughly. And then you will find a scenario like this happening. You'll see the oil on the top and the water on the bottom, and you'll see a layer in the middle that is an emulsion. So what is going on the molecular level? These 2 tails, so think of this as the oil droplet. The 2 tails are going to be stuck into the oil droplet, and the head is in the water. So think of 2 tails being stuck in the oil droplet, head in the water. 2 tails stuck in the oil droplet, head in the water. You get the idea. I'm not an artist at all. But basically, this would be one of these droplets. It has a bunch of lecithin all around it with the tails stuck in the oil because the tails are attracted to the nonpolar oil. And then the head, which is this charged part, that's attracted to the water. Okay? If you remember from intro chem days, like dissolves in like, polar dissolves in polar, nonpolar dissolves in nonpolar. So the polar portion, this part that has a charge, can dissolve in the water. But these tails that are very nonpolar, hate water, they dissolve in the oil. And so that way they suspend the oil droplets and you have a beautiful cake. All right, so that's a couple of applications for the phospholipid. We've got the phospholipid bilayer in the plasma membrane, works as a beautiful emulsifier. And now let's do the last category of lipids, and they are the steroids or sterols. Now, the only thing you need to recognize is that any molecule that has this structure over here, okay, this is called the steroid nucleus. It has 3 hexagons and 1 pentagon. This is the steroid nucleus. This is what, so cholesterol looks like this. Estrogen looks like this. Testosterone looks like this. Vitamin D looks like this. Progesterone looks like this. But how do they differ? They have other things attached to it. They could have some double bonds, some carbons coming out. double bonds, OHs. So don't worry about all the stuff, but just recognize this nucleus. So if I have a structure on a quiz or a test that you can recognize this nucleus here, it doesn't matter all the other stuff coming out of it, you say that's in the steroid or sterol category, okay? It is considered a lipid, and it is considered a non-saponifiable lipid. Why is it considered non-saponifiable? Remember how I told you guys that anything that has an ester group in it, you can do a saponification reaction, or you will be able to make soap out of it. And we're going to talk about saponification in the next video. But you can see here that there's no ester. Do you see a carbonyl O anywhere? No ester. So this is in the non-saponifiable lipid category. Sterols, steroids, all that category are all non-saponifiable. Very important. What are some uses of cholesterol? Like we talked about that cholesterol can be used to make bile acids. Cholesterol is used by the body to make vitamin D. Cholesterol is used by the body to as a precursor for a lot of the sex hormones. Cholesterol is important in the body for rigidity of the plasma membrane. So these are functions of cholesterol. A lot of people are absolutely terrified of cholesterol. They always tell you, you can't have high cholesterol. It's a risk factor for heart disease, et cetera, et cetera. But cholesterol is a very important molecule in your body, and I just went through all of its uses. Okay, so structure-wise, recognize this nucleus as being part of the steroid category. All right, so we're done with all of the what you need to know list, except for the last one, which is know some lipid reactions. We're going to talk about hydrogenation, hydrolysis, and saponification. And then once we're done with that, we are all set with this week 4 material. Okay, see you in the next one.